przykład szkoły.
It's an important debate, and I think the more people who discuss it and learn about the benefits of exploring, the better off everyone is.
No, ale jest to bardzo ważne. Im więcej ludzi się przekonuje i dyskutuje na temat właśnie badania kosmosu, to tym może będzie to ważniejsze i łatwiejsze.
So, I'm open to take your questions.
Myślę, że będzie przyprawione. Są jakieś pytania?
May I ask, thank you for your excellent wykład, lecture. But I have the questions about Venus, atmosphere of Venus, especially I think about pressure.
Yes.
The carbon dioxide is very high pressure, and if you try explain using, for example, van der Waals equation or single degree of freedom system and 6 degree of freedom system with not single mass, we have in this attempt towards absolutely different result like data analysis and evolution. How it's possible to explain how scientists try to explain this strange kind of phenomena in Venus atmosphere?
Well, the surface pressure now is about 90 times what we have the pressure on Earth's surface. How it got there is explained by the fact that Venus at some point in its early history was cooler, because we believe there was liquid water on the surface. And it's important to ask, how do we know there was liquid water? Because if we explore Venus now, you don't see any liquid water. And it came from an atmospheric entry probe that measured the isotopic ratios of hydrogen. Hydrogen, as you know, has two isotopes, deuterium and tritium. There's one extra neutron in deuterium and 2 for tritium. So, and let me backtrack. We believe all the planets formed from the solar nebula. So, a priori, the expectation is that the unevolved atmospheres should have the solar composition. And so, if Venus and Earth formed in the same part of the solar system at roughly the same time, about 4.5 billion years ago, they should have similar amounts of hydrogen and deuterium. And we know the ratio on Earth from sampling the ocean water. So that ratio, hydrogen to deuterium, is enriched on Venus by more than a factor of 100. So how do you make that ratio so high? And it's even higher above the clouds than below the clouds. So right now, above the clouds is 200 times higher. And the only way you can make that ratio is if you take water and you evaporate it, goes into the atmosphere, the sunlight dissociates, and the lighter hydrogen escapes to space, and the heavier deuterium stays behind. And so it's a fractionation process. And if that goes on for a long time, you can continue to have more and more deuterium in the atmosphere. That's the only logical explanation for it.
Thank you so much.
So if there was liquid water, then the question is, what was the surface pressure? Now, just last week, last Friday, one of my colleagues was going on an expedition to look for these bacteria on Earth to see if they could survive on Venus. They published a paper, and we now know that early Earth, the pressure was half what it is today, which is just opposite of what people had believed until recently. Because in the early history, the sun was not as warm. It was fainter, so it did not produce as much energy. And that's a problem for creating life on Earth. So the only way they could create a warm Earth was by having high pressure, more like Venus. And now we know it was just the opposite. So we don't know what the past pressure on planets like Mars and Venus could have been. It's just a guess. You try to reason, but if you find some evidence, then you have to change your ideas. So I don't know.
Thank you.